Hello, welcome to Bedroom Builds at the From Python to Rust series, episode number 4, strings. Continuing from the previous episode where we talked about tuples, arrays, and slices. Strings will appear in basically every software that you write, so it's important that you understand how they work and how they are stored in the backend. With Python 3, the source code itself can be encoded in whatever you like, but it's probably smart to use it in the UTF-8 encoding. However, other encodings are supported, as you might already know. The internal representation of a string that you will use within your software, however, will be by default Unicode as of Python 3. And the actual bytes inside will be as compact as possible. So if you do not use special characters and only stick to your ANSI and the English character set, you will end up only using 8 bits per character in your strings, especially in the European languages with accents and umlauts and whatnot. You will end up using 2 bytes per character, and with most of the Asian languages, you will probably even end up using 4 bytes per character as the internal representation in Python. In Rust, the source code is supposed to be stored in UTF-8, so this is what you should do. The strings themselves are represented as Unicode all the time. There is no other way. They are encoded and enforced to be valid UTF-8 all the time as well. This means that if you directly slice your memory wherever you want, you can actually end up with invalid UTF-8 afterwards, and this will result in a panic. So you should not just willy-nilly do memory stuff that works nicely when you only deal with, say, English sentences, because this might break in the future if somebody then uses other languages characters that end up being encoded in more than one character per byte, more than one byte per character. So this means you should use the chars iterator that exists for every string. This means it will hop for every character and not for every byte, and giving you the next character to deal with. Interesting crates for Unicode exist for further detail use. For example, for grapheme clusters, you can use the Unicode segmentation crate, and Unicode normalization can be used for comparisons. Okay, let's look into some technical details of how this works within Rust. So internally, they are actually stored as a vector of unsigned 8-bit integers or bytes. They are guaranteed to be valid UTF-8, as already mentioned. And they are not null terminated. So this is in contrast to, for example, C, where a null character would be at the very end of a string, terminating it. The reason this can be done is that a string has 3 informations. It is having a pointer into memory, where the string starts, the information of the length of the string, and about the capacity of how much the string can hold. And with these 3 informations, you can always safely know where the string ends, so you don't need a null terminating character, or therefore you also don't need to look for this, for example. And this second option would be slices or string references. So this is denoted by the ampersand and str. This can be useful, for example, passing only references to functions and not a copy of a string, for example. And those slices have to point at a valid UTF-8 sequence as well. And they can be a view into a string, for example. But you can, you will see later, also use these as a static constant in your code, for example. So you don't have to declare and initialize a string all the time if all you want to do is just use a static string. Now let's look at the UTF-8 and why it is important to not just break strings at the byte line. So how UTF-8 works is it uses from 1 up to 4 bytes per character. And the trick it uses is the first bit of a byte is 0 for the normal stuff that is within ANSI definitions. So you get your 127 characters that would be alphanumerics, and most of the other like commas, dots, and exclamation marks. And therefore you can basically write valid UTF-8 by just taking any ANSI text. That's very practical. If, however, the first bit is set, you actually expect a second bit also to be 1. And this denotes that now actually 2 bytes are used to encode the coming character. And if you want to have 3 bytes encoding the character, you will have the first 3 bits set to 1. And the same is then true for 4 bytes used per character. Then you have the 4 first bits set to 1. And on the very left, you can see how many bits you have at the end available to you to encode your coding. So you start off with 7 bits, then 11, 16. Even though you're using 3 bytes, you only have 16 bits. And then for 21 bits, covering all of Unicode space, you get to use with your 4 byte encoding. And some examples here below. The normal character A is really just using those 7 bits, so it starts here with the 1, then 0, 0, and whatever. And the umlaut A, for example, though, already needs the 2 bytes, so now we use those 2 bytes. And in binary, they would look like this, and also as we can see up here, it actually works like that, so we have the 1, 1 that denotes, oh, we will actually use 2 bytes. Then we get our code, and the second byte also has the first bit set, of course, to let the reader know, oh, this is part of our multi-byte encoding block. Then a new character, like the euro sign for the currency, was added a bit later in time, so this is ending up even in a higher Unicode block, and this already needs 3 bytes. Same idea again, the first 3 bits set, and then we use the other bytes to make up the rest of the missing bits needed. And like the clef for the music notation, this is a very special character. This ends up in the block where you would also have the emojis, for example, or some of the lesser known Asian codes, or lesser used actually, because they are of course fairly well known. And these already use 4 bytes to encode them. And here you then start to understand, if you really only split your memory at a random location, then you can actually cut this umlaut A in half, or the euro sign, you work off this one, and then you cannot decode it anymore, because those two on its own don't make sense, because the first byte already tells it should be 3 bytes long. So it expects the third one, it doesn't come, because the third one will not have potentially the first bit set, and then you break your encoding validity, and therefore it's important to use the jars iterator and not directly mess around with memory space. Good, enough about theory, let's jump into the code. Again, I tried to have the same stuff in the same lines, left and right. In Python, it is fairly easy to do a declaration of a string. You use the variable name equals, and then whatever comes between quotation marks is your string. In Rust, this is a bit more complicated, because a string is already a data structure, so you would have to use your variable name and construct a string from, and then your static string slice as an input. Below, you will already see an operation done on the string, replacing a dog with the word cat, and this looks very similar in both cases. And this way you can then have 2 strings. One is Alice and Bob, and they have the 2 different contents, because the replace will return the new string, and below we'll have the output. Next, this doesn't change in Python, because it doesn't have the concept of just static string slices or string references. And here you can see the declaration, and this funny single quotation mark, and then the text here static is also in a different color encoding. I hope you can see that. This is a lifetime annotation, and the lifetime starts always with this single tick, and then you can give it a name, and this one is a predefined name by the Rust compiler, and this means this is a static string that lives the whole lifetime of your application, and this will be written to the read-only memory of your binary. And this is the way you can actually define only this string slice. It does not have all the benefits of a full-on string, so you cannot use a replace on that. And it's also not on the heap though, because it's in your read-only memory of your binary. Then, but you can still, print it, and you can iterate over it. So you can actually use an iterator that splits it by white space and reverses it. And further down, you can iterate over the characters and collect this into a vector of characters, not bytes, characters, very important. Here we then can sort those characters, and the DTAP would make them unique, so deduplicate. It will not allow duplicates to be in this vector or list. And the same we can do in Python on the left. We would just split the string into its words. We can reverse them, and we can iterate over every element of this reversed iterator. And the print will be the same. Doing this character jumping and location collection in Python, you by default jump by character if you use the iterators like this. So you cannot even if you wanted to go over this by memory, because Python makes sure you get a character and not a byte, not the next byte. So this is doing the same. And then set I'm using as a trick to deduplicate, because a set only allows every element to be in there once. And then I would sort this, and I would have the same output in here in these characters. Below, we can then do one more trick that would be maybe interesting for string processing, is how do you add stuff at the end? How do you append stuff at the end? In Python, we just use the plus equal sign, for example. And to do this, in Rust exists the push method. And the push string method would then not only push one single character as here, but a full-on string. And with this, you can add stuff. Very important here, the mutation definition. So if you want to mutate and add stuff at the end, you would have to declare it this way. Further down, we then trim it. The idea here is that we have a slice of characters that we don't want to get rid of at the beginning and at the end of the string. And then we can use the trim matches method to do this for us. In Python, we can only declare a string or anything that gives it items that we want to trim. And the string strip will then strip those characters found in this iterable for us. Same thing. Good, let's look at the code, if it works. We will first check out Python. This means we run python strings.py, and it does the stuff that we discussed. So here it would, in reverse, give us the words. It starts with lazy. Lazy is the last word, the, and so on. Then here we get our used characters list, and you can see that it actually starts with a space, a comma, because, well, space is within this text. And then we get our list of characters used in here. And then after the trimming, so we wanted to get rid of space and comma at the end, at the beginning. And we actually do this. So we start with the A, and we do not have a final comma. Code works as expected. Let's hope this is true for our Rust code as well. This means we have to compile as usual. Then we need to run it. And we get our result in the same way. So last one first, lazy, the whatever. Then we also have our used characters. We start with the space, with the comma, we have the comma at the end. And now after the trimming, we got rid of it. So the code is really equivalent. Going back to the next file, we will now check out uppercasing stuff. That's fairly interesting, actually, because dealing with Unicode then has a very interesting issue with this. Let's see what we have in Rust. So the Rust code is a bit more elaborate, so I cannot match the lines very easily because we do, I want to show different things. At the very top, we define a function that here we will call it ASCII capitalize. So I wrote something that is customized for Python that it would only uppercase a character that is within the ASCII range. And here we have our names list. So we have first Alice, Bob, Özgül, and this is not a name, but just a presentation of a special problem that we will run into. So this is a character in German, and there is no uppercase equivalent of it. And you can actually keep it the way it is, or you're allowed to use two big normal S's and replacing this one. So this single character actually becomes 2 when you uppercase. This makes it even more important to go by character and not by memory space, because if you use just memory, you will now actually have to jump in memory by 1 doing that. Now we have here a function called naive capitalize that actually goes by characters, and if the string was empty, you will then return a new string, and if not, it would uppercase the first character and then attach the rest of the string. Then we have the ASCII capitalize, so the re-implementation of what I did in Python already. Same thing, we go by characters, and then we only use a special function now, the to ASCII uppercase, and not the to uppercase, which does it for Unicode. And then we do the same trick by appending the rest of this iterator as a string. The reason that this whole expression works is we are returning a string, and this match statement is more or less like an if-else if block. I will go into details in a future episode about this. And it analyzes the return of this see next. The next can be either none, so undefined because the string is empty from the start, for example, in this case. And then you have to handle this special case, because if it was empty and you don't get the next character, you will have to deal with it. In our case, we just deal by returning an empty string. And since this is the last statement in the code, we don't have to write return. This whole match block becomes the last statement, and it either has this line and meaning there is a new string, or this longer expression that gives us the uppercase of the character found. So some means it has found something, and then it moves the value that it found into a variable called f. This f then gets ASCII uppercased, converted to a string, and we can also use the plus sign to append to a string, and then we use the as string from the iterator that we created up here to give us the rest as a string. Concatenated becomes our ASCII capitalized string. Here we have also our list or vector of the names, so Alice, Bob, Özgül, and Sad. And for name in names, so this is a normal iterator that iterates over references into our vector here, and then we will print line first the name, how it started out, then the naive capitalize, and then the name again with the ASCII capitalization, and we check the differences. Same is then done here in Python on the left side. I used the normal capitalize because this is by default basically doing the Unicode capitalization, and I used my specialized ASCII capitalize function as the second one. Okay, let's run the code. I hope I can show both codes left and right to show how this ends up in the different thingies. So we have the Rust code now on the right side. And Python on the left. Let's clear our output on both. Then we Rust compile our uppercase code and we run it right away. And then we go to our Python code and do the same. And here we can see that they are hopefully equivalent. So Alice becomes Alice in both cases because the A is within ASCII. Same is true for Bob on both sides. However, the name Özgül becomes with the uppercase Ö correctly. So there's a big O now with the dots above, and here it's a small one capitalized. But on the ASCII code it does not, because the Ö is not an ASCII character. And here we have this special S character that gets actually to two S's here. And this is already done differently because the uppercasing means that it becomes two capital S's. And in Rust it's implemented this way. And the ASCII one, of course, does not really change the output, so it stays the same. And the reason I called the uppercasing naive for the whole thing is in languages, that's an example that is given, for example, in the Rust documentation for the uppercase function, is there is a capital I with a dot above in Turkish, for example, and it's not clear from a small I that you should do this when capitalizing to this one, because this is only true for Turkish. So you not only have to make sure that your encoding is correct, now you also have to make sure that you are working within the same language space. So this is only naively working. You might have special requirements for your language that need to be respected as well. Therefore, Unicode is a very big topic to talk about, and it's not only important to not just cut stuff at some random byte blocks. You should also make sure that it's working nicely for your target audience. Good, let's go back to the code and let's see what UTF-8 shenanigans we can actually do. So back to the Python code, and here we go back to Rust code. We can edit UTF-8RS. At first, I only declare something that is actually only comprised of ASCII characters. So we have the hello. Then we try to figure out how much space this takes up in memory. And then we print all of those details here in our printf function. And I do the same in Rust. I declare a string called hello. Then I would figure out how long it is, then how many characters it has. So this will give us the byte count in UTF-8 if you want. This gives us the character count, which will be different depending on the contents. And then with this namespace standard mem size of function and the given type, we can figure out how much the type takes up in memory. And then if I add the length of the data, then I know how much the whole string takes up in memory. So this will be an equivalent, I hope at least, of this sys get size of. Then below here, I can actually print this out in bytes. So then it's no longer characters. This is now the byte representation of our string. And then I try to be smart and use a slice into the string, directly taking the memory location 2. And I want to print everything after the character E. Let's see if this works. So this would be 0, 1, and then from 2 onwards, I want to have everything printed. Here we just make sure we know that we are now doing the second example, which now uses hello written in a funny way. So I have an accent on the E and an Ö at the end in both languages. I do the same trick again. I want to know how much space does this take up in memory. We do the same trick on this side. And then we print out this stuff encoded in UTF-8, which is the same as if I was calling the as bytes. This is very low cost in Rust because it's already in UTF-8 by default. And then I try the same trick. I want to see everything after the E Okay, in this case, it's actually after the E with an accent. And here, I want to do the same, directly going into memory and seeing the rest of my string. Let's see if this works. All right, let's run those two codes side by side to see how they behave. On Python, I will stay on the left now again, like I did before. And for Rust, we will do stay on the right. I compile the UTF-8 example and I run it. This is not what I want to do. Then we jump over here and we use Python UTF-8 py and we get our output. We can see that the hello string is a length of 5 with 5 characters and uses up 54 bytes in memory in Python. In Rust, we have a length of 5 bytes, it has 5 characters, and it uses 29 bytes in memory. So why 29 bytes in memory for Rust? As I said on the beginning slides, a string is comprised of 3 informations: where it is in memory, second, how long is it, and third information, what is the capacity of the string. And on a 64 bits system, each of those numbers are 64 bits in size. Therefore, we have 3 times 8 bytes to store this information. This makes up 24 bytes, and the length of the string is 5, so 29 in Rust. In Python, I don't really know all the details that they store in it, but it seems to be way more powerful than what we have in Rust. I guess it also stores extra information of how compact is the string, what is the format and other things. This is why it uses more memory for this tiny string than it does here in Rust. The binary representation in Python starts with this B. So if you want to declare it in Python, you also use the B. And then everything that comes between the quotation marks is now your byte sequence and no longer a Unicode string. In Rust, by default, it gives you a vector of unsigned 8-bit integers. Therefore, you see a vector with those numbers and not something that can be directly printed. And here we see the output of our example where we use the square brackets with a range to get us a slice out of the string, starting with the index 2. So we get our LLO fine, and the same works here in Rust as well, because since we don't use any special characters, we actually get a valid UTF-8 out of this, and it works fine. Now the hello with the umlaut E, with the E accent and the umlaut O, gives us in Python as well the length of 5 and the characters 5, because there is no difference from the point of view in Python. However, the memory size is much bigger now. The biggest memory usage was explained at one of the beginning slides, where I said that Python tries to store a string in the most compact form possible. However, for ASCII, it stays at 1 byte per character, but for anything special, it will jump to 2-byte representation or even 4-byte representation per character. So now we also store this H in 2 bytes, the E, the L, and everything, and this is why it grows drastically between those two strings. In Rust, you can see it's only 2 bytes more. The reason is, in memory, this is represented as UTF-8. And remember from the example page that this is now stored with 2 bytes and this as well. So 2 times we add 1 byte to our storage requirements, making the memory length 7. Characters stay 5. And now this also means in memory we use up 2 more bytes. You can also see these are now here at the end, added. Printed in Python, you used to have the B for binary string, then the H is actually a readable character. Stuff that is not printable in ASCII will now be shown with the \x escape. And then we have our 2 L's, and then we have the umlaut O encoded here. If we use our slice, it works fine in Python. We get the LLO at the end. However, as predicted on the slide, if you just jump in memory and try to make a slice out of a UTF-8 string and it's an invalid one, you will end up with a panic, and this is shown here. It even gives you a fairly well information of what happened. So you actually try to slice into the E accent, and it didn't like it. Now we can jump to the last example, just looking at how multi-line strings are declared and work in those two languages. Let's quickly hop back to where we were. So we have our Python code on the left now. This is not good. So Python on the left and Rust on the right, exactly. Now let's switch over to our new multi-line RS, and we will have the same in Python. In Python, you can use for multi-line strings the 3 quotation marks in a row, and like here at the end and up here at the start. These can be the double quotes or the single quotes. The advantage is if you swap the quoting to single quotes, you can use double quotes inside your single quotes and it will not end the string. It will be basically escaped. You can use a single quote within the triple single quotes. That's very practical. In Rust, you are limited. Strings are always using double quotes and single ones of those. So if you want to have multi-lines, you can use it this way. A bit convoluted, but this works. Then here is a new way to declare a string. You can use the static string .toString method and it will end up being a string object. And if we want to escape, then of course, if I now want to write the same expression that I have here on the Python side, I would have to escape the double quotation marks. Single quotes within the double quotes work, however, and then we have a new line sign, a character, and our test. This now also gets then toString and printed. The single quote is only used for declaring single characters in Rust. So while this works fine as declaring a string in Python, this will actually now fail. Let's run the code. Run the Rust compiler on our multi-line code, and it tells me that I cannot do what I already explained. This has to use double quotes for a string, or I can declare a character with the single quotes. So let's quickly fix the code. I will just remove one of the two. Then you can actually also see the color coding changes in the editor. So running the code now again, it will warn us of unused variables and stuff because this is just to demonstrate multi-line string encoding. This was my introduction into strings in Python and Rust. Thanks for watching. Coming up next in the From Python to Rust series will be functions and closures.